All right, well, I'm recording now, so we can get started. We did the water pressure, and I said we'll start this one again, the water pressure level. Uh, what our water pressures need to be in order to get water to where we want it to be. So if we think about Texas, they didn't have water pressure in the pipes to get the water to their house. The pipes burst because of the freezing temperatures, and therefore the pipes burst and they didn't have pressure. But the pumps burst. If the pipes didn't break, the some of the pumps did, so they didn't have pumps to make water pressure. So again, the same result. They didn't have water, and now they're seem to be back to normal temperatures, which is good. So anyway, we want to talk about getting water up to the last fixture, wherever it is in a facility. But let me double check to make sure you're seeing my PowerPoint screen and you can hear me.
Yes, Professor, we can hear you, but there's no PowerPoint presentation.
All right, so that's my fault for not sharing the screen.
Also, I have a question, Professor. Last week, did you record the lecture?
I did.
Did you post it on Blackboard?
I might not have. I know it's recorded, so I'll post it today.
Okay, thank you, Professor.
It takes a while to convert it, but that's no excuse for waiting a week to get it up there. So I saw it today. It's up. It's in my folder, so I'll just upload it. Maybe during the break, I'll try to do that. It takes a while for YouTube to process it too, so it won't be there immediately. But anyway, we'll get it up there. So, any other questions before we get started?
Professor, when do we have the exam?
Well, we can't have the first quiz until we get through the material on the first quiz. So unless you want to take the quiz ahead of time without having me cover the material, which I don't think you do. So it's flexible. I'll definitely give you warning about it before.
Is it going to be a time limit for the quiz, or how is it's going to work?
There's no real time limit in terms of how long you have to take it once you start, but there is a drop dead finish date, which generally is you have 4 or 5 days minimum to take the quiz. Okay.
Once we start, and it's going to be a certain time to finish?
No, it's going to be a certain day where the quiz will close. So let's say that I was going to have the quiz open up today at the end of class, which is not true, so don't worry about it. But let's say it opened up today at the end of class, it would close probably around Wednesday or Thursday, which would give you plenty of time to take it. And there's you can take part of the quiz and then come back and take other parts of it. So you do not have to finish it all at one sitting.
Oh, I see. And Professor, for the attendance, I mean, there is no option for me to click and open to take the attendance.
Let's see. Let me look there real quick.
Please.
In the group section, and it's February 26th, and 10 people have already signed in. No, yeah, 10 people have already signed in. So go to the group section, look in the folder with today's date.
I got it. Thank you, Professor.
Okay.
I appreciate it.
Anything else before we get started? Okay, so let's do this again. The power, let me turn on the chat just in case somebody wants to chat. Let's see, where is that? More chat. Okay, just in case anyone prefers to write their comments in the chat box instead of verbalizing it, that's fine. So anyway, we're talking about water pressure, that's where we left off. And we left off at this last question here. And I said we'd do it again. So basically what we want to do is we want to, this is kind of, if you saw this on a quiz or an exam, this is exactly how you might see it with this particular information given to you, okay? Maybe this would be given, maybe not. In other words, I might be a little tricky and not give you the equivalent length, but you would have to add that in there yourself. I might not remind you about the equivalent length, but you would still have to add it. And remember, the equivalent length is whatever the length of the pipe is, loss in pressure, we're going to have that same loss in pressure for the bends and the curves and the fittings and the fixtures. So you might want to pay attention to the question and ask yourself, did Professor Bryce give us the equivalent length? Or do I need to remember that there's the equivalent length added into the numbers that he's given us? So I might be a little tricky. I'm not going to say which way it is. It might say that it includes that and it might not. If it doesn't include the equivalent length, the question I mean now, I'm not going to say the question does not include the equivalent length. That just means that I expect you to add the equivalent length into your calculations. And so the water pressure across the water meter is 5 PSI. So that means that when we, do I have a, no. Okay, so let me make a quick duplicate. We'll make a new slide and see if I can draw on this. So I'm going to insert a symbol, which would be a circle. So we'll put a circle in there. All right, we'll put an oval in there. And I'm just going to put that oval in there. And then I'm going to insert, I'm going to draw some lines. Do we have lines to draw here? Pictures, shapes. Okay, maybe lines. Yeah, there we go. There's, no, that looks like it might be an arrow. All right, here's lines. Okay, so this might be a little better in terms of, let's see how that works. Okay, so then insert shapes, lines. Now we're going to go vertical. And then we're going to go, nope, that doesn't do it. Insert shapes, lines, and then we're going to come across like that. Okay, so this is the meter. So let's insert the letter M in here for meter. Okay, and now let's take a look at what we have, because I think the best way to answer this problem is to actually draw a real quick diagram of it. So this is much better than we had last week in terms of the graphics. All right, so back to question 1.3. The water pressure across the meter is 5 PSI. So here we're going to write minus 5 PSI, okay? And let's just see if I can grab this guy and drag him. All right, anybody want to help here? Oh, here we go. I think I saw it. Oh, nope, that's the whole thing. I'm trying to move this down over here. It's not letting me put the text box down here, and I don't know why. There it is. There's the text box. Now let me move it over to where I want it to be, which is right here. So we would say minus 5 right here. We're losing 5 PSI at the meter. Okay, so that's great. Then let's go back to the next thing. We're losing the pipe lengths. We're losing 15 PSI. So we're going to come over here and let's see if it'll let me do that now. Insert a text box. and we'll put it, I don't understand why it won't let me do it. Oh, all right, we'll grab this guy. And we're gonna say right here, for the pipe lengths, we're losing minus 15 PSI. All right, but oh, geez. There we go. So we're losing minus 15 PSI for the pipe lengths, okay? So we got the first two, but now remember we have the equivalent length. That's all the bends and everything that are in there. So we have to duplicate this, whatever that is, for the length of the pipe. We're going to also, oh, geez. Have to put that down here. Oh gosh, it's not working for me. And I'm trying to show you this in a more, I want to copy this guy right here. There we go. So again, we have to subtract another 15 PSI. Why? Why am I deleting that or subtracting it twice? Somebody tell me.
Because it's going through the pipes fittings, we're losing the pressure.
Absolutely. Remember, we have the length of the pipe, but we also have the bends that occur in that pipe. So there might be some bends in the pipe as well, and we have to accommodate for that. And basically, what we say is whatever the pressure loss in the length of the pipe, we're going to actually have the same pressure loss because of the bends in the pipe. So that's absolutely right. So we might have something like that. I don't know how to break this guy up. We have to pull him back like that. All right, I think I'm getting the hang of this now. All right, so there we go. All right, so we lose 15 PSI just for the length of the pipe, but we also lose the exact same amount, the equivalent length, for the bends and the fittings and all of that. So that answer was absolutely correct. Then let's see what other information is given. The water pressure at the water main is 53.9 PSI. So that means that we have insert text box. Yep. So here, what did we say? Plus, that's going to be a plus 159, I think it was. I'll double check that right now. No, 53.9, not even close. So let me change that to 53.9. So that's a plus. So the water that's coming into the water meter is coming in at a pressure of 53.9 PSI. Then we lose 5 PSI at the meter. Then we lose 15 PSI for the lengths of the pipe, but we have to double that because of the bends and the curves and the fittings and everything. So we subtract another 15 PSI. And then we need a minimum at the end of the run of minus 15 or 25 PSI. We have to have a surplus. So again, another text box over here of minus 25 PSI. And then what's left? The minimum water pressure left to flush the highest fixture is 25. So the question is, what's the maximum height? So here's the question. How high can this be? What's the value here? So that's going to be, we want to solve for X. All right. So the question is, what is X? So how would we solve that? All right, I put that all together. Plus 53.9 minus 5 minus 15 minus 15 minus 25 is going to leave us how much? Oh, this is 1.3. All right, so the height of the fixture above the main is 300 feet. All right, so we know that the height of the distance is 300 feet. So if that's 300 feet, what's the water pressure loss there? Uh, 300 feet. So what's the water pressure loss for 300 feet of vertical rise? Does anybody want to suggest what that might be? How we could figure it out? It's 300 times something. What is it? Nobody?
0.433.
Absolutely correct. Remember, we
Yeah.
gave that information back at the slide last week. For every foot that we rise up of water, we lose 0.433 of PSI. So in this particular case, we're saying it's 300 feet. So we multiply that times 0.433. Okay, and what is that? Anybody have a calculator to do that?
Ooh, 129.9.
Exactly. Perfect. Equals 129.9. And that's a minus 2, isn't it? Because that's a pressure loss. So let's put a space there. Okay, so we lose minus 129. Let's see what the question is now. How much extra water pressure are we going to have to provide? What is the minimum pressure boost required of a pump? All right, so we're going to say minus 5, minus 15, minus 15, minus 129 for this distance, minus 25. When we add all of that together, what do we get?
$189.9.
So let's do it. Minus 5, minus 15, minus 15, minus 129.9, minus 25. And we have to add a number. What number are we going to add to that?
Are we adding the 53.9?
Absolutely, because that's the pressure that we start with. Okay, so I'm going to double check that just to see what we have there. I got minus 5, minus 15, minus 15, minus 129.9, minus 25, plus 53.9. So 136 is what I get. Does anybody get something different?
Same.
Yeah, 136.
Let me double check that. Okay, so I'm going to say minus 5, minus 15, minus 15, minus 129.9, minus 25 equals 189, right? Plus 53.9. I got to put a 3 in there. I missed that. So plus 53.9 equals 136. I get 136 again. Somebody got something different?
No, I got 136.
Yeah, minus 5, minus 5, minus 15, minus 15, minus 15, minus 15, minus 129 for that, minus 25 for that, plus 53.9 for that equals 136. So the answer to this question would be that we need 136 PSI of additional pressure. And how do we do that? With a booster pump, with a pump that will increase the water pressure. And that's how we would do that. So does that make sense? Anybody have any question about that?
That's good.
All right, so you're probably gonna see something like that. I am recording the class. Somebody asked that in chat, and yeah, I am recording it. Yeah, so that's good, but thanks for reminding me. All right, so let's move on then. If that's good for everybody, I'm gonna save this and leave that drawing in there. If we have to go back and review it again, at least we'll have that to look at. Okay, so let's go to the next one. All right, so the materials did we talk about materials already? I think we did.
Yeah, I think we did two.
Yes, you did.
Yeah, basically the confusing part is that we have heavy wall type K, medium gauge type L, and light gauge type M. So and common is the most and type L is the most commonly used, and copper is the most commonly used material. Now, when we get into the plastics, you really want to stay away from that in your water supplies. And many municipalities will not let you actually use plastic pipe for your water supplies for many reasons. And one is that it could very well be off-gassing some kind of slight chemicals that you don't want to introduce into your drinking water or your washing water. The Flint debacle, they couldn't wash in their water. They couldn't wash their clothes themselves. They couldn't drink the water. They got sores on their bodies. They got lead into their bodies. The kids got permanent brain damage because their brains hadn't been totally matured yet. They were still growing. It's a terrible disaster, and people died. So, you know, adding chemicals into your water, you want to be very careful about that. And though the chemicals might be very minute in terms of the chemicals that are actually going into the water from the plastic pipes, it's probably better to avoid that altogether. You're probably safer in that respect. So then we have to regulate the flow of water. Sometimes we don't want all of the pressure that we have going into our system. Sometimes we don't want any of the water going into our system. And we use things that are called valves in order to prevent or reduce the flow of water into the remaining piping system in our house or our facility. And I'm sure you've all seen a valve at some point in time or another. And if you haven't, might not be a bad time to go to one of the big boxes, Home Depot or Lowe's, or your local hardware store, and just take a look at some of the valves that they have in the plumbing department. Now, a gate valve is designed kind of like you would think. It's designed to be fully open or fully closed. So either the gate's open or the gate's closed. If the gate's closed, the water's not going to be able to get through. If it's a fence, it's a gate keeping animals in, they're not going to be able to get out. Or the gate's open and the animals can get in and out, or the water can flow through. But that's not something that we would want to use to regulate the pressure or the flow of water. We really use a gate valve as an on-off. Yes, no, X, O, or X and one kind of a thing. If we're talking about computers, it's either on or off, okay? It's not partially on or partially off. It's either open or closed. That's a gate valve. Now, a globe valve, that's designed to regulate the flow of water. So we can actually slow down the flow of water. And that a globe valve might be the kind of valve that you see on the, similar to what you see on the outside of your house. When you're trying to wash a car and you put the hose up to that, you can regulate the flow of the water. It's not just on and off, but you can get a larger flow of water into the hose or lesser flow of water into the hose. Now, an angle valve is exactly what it sounds like. We just have an angle on the valve. So the water's coming in one direction and then going, turning a corner, maybe going off on a 45 or a 90 degrees or whatever degree the valve is, but it's an angle valve. And that's pretty simple to comprehend. But a check valve starts to get a little bit more important, and that's not where we go get our paycheck every week. It's a check valve, which will only allow the water to flow in one direction. So we'll be looking at the diagrams of this in a moment, but it is a backflow preventer. In other words, it will not let the water flow in two directions. It will only let it flow in one. And if you look at the valve, generally there's a little arrow stamped on it or molded into the valve that actually shows the direction that the water will flow. And so that's a check valve. And a pressure relief valve is something that you might see on your water heater because we don't want the pressure in the water heater to get too high, or in your boiler in your house. We don't want the pressure to get too high, and it has a setting on it. It allows it to open up in the event that the pressure exceeds a certain set point. And that depends, the set point is the point that you're telling that valve to open up and relieve the pressure of whatever device you're trying to relieve the pressure from. And that's a pressure relief valve. So if you look in your next to your water heater or close to your water heater, you should notice that there's a floor drain there. And the reason there's a floor drain is in the event that that pressure relief valve opens up, it's going to pour water onto the floor. And we want that water to be able to drain away. And that's what the drain is for, so that the water will drain into the floor drain, as opposed to flooding wherever that water heater is located. Same thing with your boiler. There's probably a drain somewhere in the floor close to your boiler, or it's actually piped right into the drain. Okay, so that the pipe that comes out of the water heater or the pipe that comes out of your boiler actually is diverted right into the drain, so the water won't actually flow onto the floor. And that's a little bit better system, because unless the drain backs up, you're not going to get water on the floor, which is not, in almost all cases, that's not a good thing, to get water on the floor in wherever these devices are located. So we have some different types of valves. And we're going to show pictures of it in a moment. But a ball valve is really, it's more like what you see in your bathroom faucet. Delta faucets make a lot of these type of valves, and it's really just a ball with a hole in it. And as you move the handle on the faucet, it locates that hole so that there's more water flow or less water flow that can be allowed to flow through it. And that's just called a ball valve. And it really is a ball with a hole in it, that as you locate the ball over the water source or supply, the more that hole is aligned with the water source or the water supply, the more water that can flow through. And if you go to the faucet section of the big boxes or your local hardware store, you'll be able to see how the ball valve works, or they may have replacement parts, because that is a replaceable part in the faucet. And you might just be able to look at the replacement part and see the actual ball valve itself. Now, there's also pressure reducing valves, and that's just a valve that's going to reduce the pressure of the water. And so we might want to put that in rather than have the pressure increase beyond the capacity of the equipment that is attached to, or the pipe that it's within. Now, a vacuum breaker, it is another way that it prevents the backflow of water. And when the atmospheric pressure, the atmospheric pressure is essentially an almost a constant. It changes slightly, but when the water pressure drops below the atmospheric pressure, then the valve breaks, or the vacuum breaks, and it'll prevent the backflow of water or sewage, depending on what is connected to it. And then we have the backflow preventer, which is very much like a check valve, and the RPZ, which is a reduced pressure zone. It's a relief valve between two check valves. So if either one of those check valves fail, then the relief valve will take over. So let's take a look at some of the pictures here. we have the gate valve and we said that's on off, either totally open or totally closed is how that's designed to function with the water. Now you might want to you might have to use that as a regulating valve, but that's not what it's designed for, but it might work. And what happens is as you turn the handle around, this comes down and it comes down in seats and stops the water from flowing through. And the angle valve that we talked about, the water's coming in here and it's going out there, so it's an angle. And you might need to have something like that in various locations in your house. And the globe valve, it's basically operates the same way. It's open or closed, and it allows the flow of water through there. But the check valve, now if you take a look at the check valve, it's not mechanically operated. It's hinged right here. This disc is hinged right here. And when the water flows this way, the hinge allows that to open up and let the water flow through. But if the water is trying to flow this way, then it'll automatically close. The pressure of the water will simply close that valve. And the reason that we might want that is the water on this side might be a different value than the water on this side. And this water is, we don't want this water, this bad water, to turn around and come back into this supply line. And that's kind of what we're trying to do. So imagine that this were a sewer line. This is the sanitary sewer line in your house and it's coming out this way. And then all of a sudden, for whatever reason, the pressure on this side is higher and the sewage is wants to go this way. Well, that check valve is going to close and prevent that backflow of the undesirable sewage or water that's going through there. And that would be something like a cross connection, and we don't want that to happen. We don't want the fresh water and the sewage water to be connected. So we do have sometimes we want to insulate that pipe. There's a couple reasons why we would want to do that. When we talk about the moisture content in the air, it is relative, the capacity for the air to hold moisture is relative to its temperature. So if you have warm, moist air in a space and you have a pipe that is traveling through that warm, moist air, but the pipe is cold, then what's going to happen is that pipe is going to cool the air that touches the pipe. And as the air cools, it doesn't have the ability to hold as much moisture. And so that moisture will appear around the outside of the pipe. And we don't want to see that. So we put some insulation around it so that we don't cool the air that's surrounding the pipe and get that condensation or that moisture on the outside of the pipe. Another reason is that we don't want, if that pipe is in a place where the temperatures might drop below freezing, then what would happen is the liquid inside of the pipe may freeze. And we all know what happens when water freezes, it expands. And if it expands enough, then it's going to burst the pipe. And that's a bad thing too. So that would be another reason why we might insulate it. And another reason is that we have heat inside the pipe and we want to keep it inside the pipe. So we might want to do that. Or the pipe might be really hot and there are people around it. And so we don't want that temperature, that hot pipe to be touched. So we put some insulation around that. So we can lose heat and protect it from the heat loss, or we can protect it, people from touching the hot pipe. So there's a few good reasons there. And here's something that some of us may be familiar with. When you close down a faucet and you hear the banging of the pipes, what's happening is that you have a pressure of the water coming into the faucet, and then you immediately stop it, but that water's still moving. So now it's going to bang into that fixture. And we call that water hammer. And when you suddenly turn the water off, sometimes you're going to hear that sound. So some of the ways that that can be eliminated is if you look under your kitchen sink, you may see a vertical pipe attached to the supply line to your faucet in the sink. And that vertical pipe doesn't have any water in it, it has air in it. And so when you quickly shut the faucet down, the air compresses, the water pushes up and compresses the air, and it acts as like a shock absorber, kind of like the way the shock absorbers work on your car. And it absorbs the shock, and so you don't get that water hammer. Or you can have something like this, which is a diaphragm, which I've never seen one of these, and oh my God, I said 70. I'm 67 years old. I've never seen one of these, but it could happen in that this diaphragm can expand as the pressure increases. That diaphragm will just get larger, and it'll absorb momentarily absorb the additional pressure, and it will stop the air hammering from happening. So if you have a lot of air hammer when you close the faucet, you look under your sink, then you probably don't see one of these vertical pipes or a rubber diaphragm. But if when you shut the pipes off, when you shut the faucet off and you shut it off quickly, and you don't have the water hammer and you look underneath the sink, you're very likely to see some sort of a shock absorber in terms of a vertical pipe or in terms of a rubber diaphragm or something like that, which allows the air to compress and absorb the pressure, the increased pressure, as opposed to hearing that water hammer. Has anybody ever experienced a water hammer in their apartment or house? Or their parents' house or their friend's house?
No, I have
No,
not.
Interesting. All right.
Say that I have. No.
they usually in the building. If like most of the Brooklyn building, I heard it before the hammer shocking.
You might find it in the older buildings. In the newer buildings, the plumbers would know to put that in, or they're required to put that in. So the newer buildings will probably see this, and the older buildings might not. So some of the older buildings in Brooklyn, that's might be where you're experiencing it. But you probably aren't going to experience that in any kind of newer buildings. And I'm talking about in the last 20 or 30 years, or even older than that. I would still consider that to be a newer building relative to this concept, that they would still have that inside of it. So what we have is pipes that are going horizontally. If you have a chance to go down into one of the subway lines and you look up to the ceiling, you'll see all kinds of pipes running across the ceiling. And those pipes are not able to support their own weight over a long distance. So that's what we use pipe supports for. And they just simply are fastened into the ceiling or a vertical member like a column or something. And it's a support for the pipe so that we can span longer distances with that pipe because the pipes themselves would not be able to support themselves for a long distance. And we just simply put some pipe supports. So one of the advantages of taking the subway is that there are, you're going to see valves like we talked about, and you're going to see pipe support like we talked about. And you can actually see them in real life. Now we'll talk about expansion and contraction of the pipes in a little bit, but the materials do expand and contract relative to their temperature. So as you heat, I'm not going to say which it is, we'll talk about that when we get to the formula, but as materials get, and you might know this from practical experience anyway, but as you heat up or cool down a material, it does expand or contract. It's not necessarily a huge amount, but over a really long distance, then it starts to make a difference, okay? So what Dr. Edwards is saying here is we do have some expansion and contraction of the pipe as the temperature changes. So is there anybody that when they get up in the morning and turn on the bathroom sink, they have to wait a little while before they have hot water? Does anybody have that problem?
All the time.
Yeah.
All the time, yeah.
Many people have that problem.
Not a problem ever. I don't experience that problem.
Well, there's a couple of reasons why you might not, and that's your source of hot water might be very close to your sink. That's one thing. You might have it insta-hot, which means your heating system is right there at the sink. Or you might have a hot water recirculation system. And when I built my house, I put that in because my hot water tank is in the lowest and farthest distance away from my master bathroom sinks, which are in the highest and again opposite and farthest direction away from the water heater. So if I did not have a water recirculation pump on my water supply, then what would happen is I would have to wait for that hot water to go all the way from the water heater up into the first floor, all the way across the first floor, up through the walls, up into the second floor master bedroom sinks. And so that could take a long time. But when I built my house, we put a water recirculation pump on there. And what happens is it's constantly recirculating hot water through a water line so that whenever I turn on the faucet, there's hot water right there. So let's see if I can go back to this page. Let's see if I can do that real quick. So let's see if I can just copy this and paste it. Okay, and I'll move it over here. And we're going to change that to I want to change that text to the water heater. I'm going to just change that text to WH. Let's see, that won't do it. All right, assume that's the water heater. And I'm going to draw a line all the way across. And then I'll draw another line. Down. And then another line across. And we'll just do it like that. Okay. So what's happening is there's a pump and it's pumping the water, the hot water from the water heater, not the meter, and it's pumping it across like that. And then it's pumping it back and then it's pumping it and it's recirculating and taking more hot water and around and around and around. And then off of that, is my sink. Okay. So there's my sink. So anytime I turn on the faucet at the sink, that it's going to drag or draw the hot water, which is in the pipe right here. And so all day long, even though no one's home, it's circulating that hot water so that whenever I decide to hit that faucet, I'm going to have instant hot water there. The other way is if I would put the water heater right next to the sink, that would work, but that you don't want the water heater in the master bedroom or bathroom. The other thing is they have the Insta-Hot heaters, which you could put right in this pipe right here. And as the water flows through that heater, it heats the water up and you have instant hot water there. So that's the recirculating. System, a pump used to recirculate hot water left in the pipe back to the hot water storage tank then back to where the sink is, then back to the water tank. And then whenever you turn the faucet on, you've got your hot water. Now, when you think about a pipe being manufactured in a factory, if you've ever been in most factories, you're going to look at it and you're going to say, wow, this is dirty. So the dirt that's in the factory is also going to get inside the pipes. All right. And when the truck comes to the factory to pick up the pipes, they're not going to wrap those pipes and keep the inside clean. They're going to convey those pipes to the job site or to the warehouse and then to the job site. But if they're taking it to the warehouse, what's going to happen? The warehouse is not immaculate. It's not an operating room. So there's going to be dirt and dust get inside of the pipe there. And then once the pipe gets to the job site, what's going to happen? Well, it's going to sit on the job site for a while. And, you know, on job sites, there's a lot of dust and dirt floating around. So what happens is that eventually the pipes are going to be connected, but they're not going to be connected with a clean interior. There's going to be things inside of that pipe that we do not want to have in our water supply. So what we do is we have to purify that water. And the way that we do that is after the system is all connected, before we actually fill it up with water, we do a test. And an air test is very simple, a way to find out if there's any leaks in the system without testing with water. So what we do is we pressurize the piping system, and then we put a gauge on the end of the pipe and measure what the pounds per square inch of pressure is inside of the pipe system. And then we go away. And we can come back. I would definitely come back more than 15 minutes, but we could come back, say the next day, for example, and take a look at the gauge to tell us what the pressure was. If the pressure is exactly the same as it was when we started measuring it, and then the next day it's the same pressure, then we know, okay, we don't have any water leaks. And that's the thing. At the apartment building that they built next to me a few years ago, very, right on the Hudson River, very beautiful, expensive apartments. They built it from scratch. And the story that I was told was that the plumber in the project got mad at the general contractor, and he put the plumbing system together, but he didn't seal any of the connections. And so what happened was the general contractor, and I watched them build this project, and I didn't think much of the general contractor in terms of coordination. You know, he would start other parts of the construction process before previous parts were done. And so it was like the next phase couldn't complete their phase because the phase before them wasn't done. And then the phase after that couldn't complete theirs. And it looked like a real uncoordinated mess. So, you know, I never I did actually meet the general contractor because I did one of the office spaces in there. And I didn't think much of him when I met him either, but he was a nice person. I just didn't think he was really that much on the ball. And it turned out that he wasn't, because the plumber put all of the pipes in this I don't know, 5-story apartment building by I don't know, an eighth of a mile long. Is a really long place right on, you know, it jutted out into the Hudson River, one of those projects. So it was a long project and a lot of units in there, okay, is what I'm trying to convey. And then when the plumber was done and the cabinets were installed and the sinks and the bathtubs and the showers and everything were installed, the general contractor did not do the air test. And the reason I know he didn't do the air test is because he just filled the pipes up with water. And he filled them up with water on a Friday night. And so when the fact that the connections didn't have any a seal on them meant that all of the connections leaked water. And when the workers came back on Monday morning to continue working, they opened up one of the access doors on the first level and water came flowing out. Tons and tons and tons of water. And the apartment units had collected, many feet of water in their units because the plumber didn't correctly install the pipes. And that's the most severe example I've ever heard of where, the plumber didn't seal any of the connections or most of the connections. He just screwed them together or put them together and didn't glue them or use any kind of fastener or sealant on any of the connections. And so what had to happen was they had to go back in and, the cabinets were destroyed, the expensive cabinets in many, not all of the units, but many, I'll use the word many, were destroyed. So all of those brand new, fresh, beautiful, expensive cabinets had to be thrown away. The gypsum board on the walls, what had to happen there? Well, that was all destroyed. So they had to at least cut 3 or 4 feet of the level of the gypsum board off in all of those units, which meant that they had to put new gypsum board in, which meant that they had to repaint, which meant that they had to put in new cabinets, buy new cabinets. And it was a real disaster, not only from a destruction of the materials inside of the apartments, but it delayed the opening of the project by several months. So the owner of the apartment unit lost revenue because they couldn't rent out the units until they were redone. So that's the advantage of this air testing is if that contractor had simply done the air test before he put water in the pipes, he would have realized that the pressure dropped significantly from the time that they started measuring the pressure till the time they came back and measured it. And they would have known that they had a problem and they would have gone and found it. It's much easier to find that you have leaks in a system using air, because if the air leaks out of the system, it's not going to cause any damage. But if water leaks out of your connections, it is going to cause damage, and it did in that particular case. So that's the testing before you put the water in. And after you put the water in, then you're going to put that water in with some sort of chlorine. And you'll either have 50 parts per million of chlorine and make it sit for 6 hours. In other words, you'll fill the pipes up with water that has 50 parts per million of chlorine in it for 6 hours, or you can increase the level of chlorine to 200 parts per million and just let that water sit for 2 hours. But I don't see any reason not to let it sit a little bit longer. And then you open up the water supply and let the system get flushed out so that all of the chlorine gets flushed out. But what happens is the chlorine kills the bacteria, and the flushing out of the chlorine also flushes out, in theory anyway, the dust and dirt and all the other particles. So any contaminants that are in there, the chlorine will take care of, and then just letting the water run for a long period of time will actually clean out the insides of the pipes before people start moving in and actually using that. So I'm wondering, are there any questions or comments or examples of disasters that you've had with water pipes in your facilities that you work in, manage, or actually live in?
I used to have an appliance repair company. I had a client that had an empty 2-story house in the wintertime, and apparently the water was on and a pipe burst in the upstairs and flooded the kitchen. Upstairs bathroom flooded the kitchen and living room and destroyed almost everything.
Well, good business for you, right? But bad news for him or his insurance company. So
Yeah.
we saw a lot of that. Well, I did anyway. On reports from Texas, people's pipes were bursting inside of their house, and or the apartment above the pipes were bursting, and there's a lot of damage done from the water flowing into their houses or apartments. So water is definitely important in our life, but it doesn't always act as a friend, if we don't treat it properly by putting in the proper equipment to take that water where we want it to be and protect it from freezing. So, all right, well, so you've had some experience in that. You know, water does do a lot of damage, and we want to be very cautious about that. But this is a good point in the presentation. It's 5 o'clock. We can take it's 5:01, so we'll take a 10-minute break, and I'll pause the recording now so we don't have 10 minutes of blank air in the recording. But if somebody could remind me when we come back to start the recording, just in case I haven't, that would be nice. Okay?
Professor, can you go back on one slide?
Sure.
Thank you.
Oh, this one? Or this one?
No, the one that the 36, page 36, page 36. There you go. Yeah.
Yeah, we passed over this one. We'll come back to that after the break. Okay?
Okay, okay, gotcha.
Yeah, that's just because this is a very important page. I'm glad you noticed that. All right, so I'm going to pause the recording now. I am recording. Okay, there we go. Thank you for reminding me of that. I appreciate that quite a bit. Okay, so even the least competent of people would do an air pressure test, especially in a multi-million dollar project that generates cash based on the occupancy of the units. That was a horrible oversight by the general contractor in that particular case that I mentioned right before the break. So I was reminded that we skipped over a slide, which is a pretty important slide, actually. This is part of your project requirements. And some of the information on this particular page. So I'm glad that we did come back to it. So we're talking about piping now, and a fixture unit. And I'm probably going to ask you, what is a fixture unit on a quiz or an exam or both? And your answer to that is that it's an arbitrary unit of water flow. It's not a given mathematical number. All right, so we don't say that a fixture unit has any kind of value relative to an actual flow of water. It's an arbitrary number, but that arbitrary number is used to identify water usage, and the more water usage that a fixture has, the higher the fixture unit would be. So if we took a look at a bathtub, it has a fixture unit of 2, whereas a water closet or a toilet, that's a fancy name for a toilet, has a fixture unit of 6. So we can take a look at some of these things. In a drinking fountain, which I started teaching at City Tech in 2006. And for the most part, all of the water fountains in that school weren't working then, and they are still not working the last time I was in there, except for the one by the cafeteria, which works but has very low flow of water. But you can see anyway, even if it did work, the water fountains did work at the university campus there, especially in the Voorhees building. The fixture unit attached to a drinking fountain is pretty low. Okay. So I'm not going to ask you to apply fixture units to the project, but remember that house plan that we looked at and started doing our heat loss calculations for. We're also going to have to do some pipe diagrams, which we should get to today. If not, we'll get to a riser diagram, it's called, and we'll get to that by the following week. But I'm not going to ask you to tell me what kind of pressure minimum PSI we need for these kind of things. But you can see that a toilet needs a pretty high amount of PSI, whereas a drinking fountain doesn't need a lot of PSI. But we will want to know what the trap size is. So when we get to the riser diagram, which is appropriate for this project, your final project, you'll want to refer to this, the trap sizes that are required for the various fixtures. So if there's a bathtub, you're going to need a 1.5 inch minimum trap. And if it's a shower, you're going to need a 2 inch minimum trap. And I had a good friend who built a summer house in Southampton, a very beautiful summer house. And he was really quite excited about the quality of the house because he was the general contractor. And he did a really wonderful job constructing the house. I was not the architect. He didn't know me at that time. I think maybe I would have been the architect if he had known me when he started. But I met him at the final phases of his project, his house, and gave me a beautiful tour through it. And it was really, really nice in every way until I got to the master shower, which would, I'm going to guess the shower in the master bedroom was, 8 feet by 6 feet. And I might be a little bit high or a little bit low, but he had all kinds of body sprays and the rain heads at the top, and handheld sprays and all kinds of ways that water could come out on the occupant or occupants of the shower. Huge amounts of water were flowing out, and he had solid pieces of marble. There were no joints. These were one piece of huge slabs of marble, creating the walls of the shower and the ceiling. And I was quite impressed by it. It was really quite a beautiful shower and big. I mean, excessively big, way bigger than it needed to be, and overloaded with all of these body sprays and different ways that water could be sprayed on top of the occupants of the shower. And then I looked down at the drain, and he had just a regular drain in the bottom of the shower. And I said to him, Jim, I hope you don't plan on turning all of these on at the same time. And he said, why? And I said, well, you've got, 5-10 gallons of water flowing into your shower every minute. And you've got 2 gallons of water being able to be drained from it. The net result is going to be, you're going to have water accumulating on the floor of your shower. But it was too late. He couldn't have the plumber put in more drain capability because it was already all that beautiful marble on the floor as well, and he couldn't break that up. So although he had all of these wonderful things that he could use in the shower for water supply, he couldn't use them all at the same time. He had to be very careful about which ones he used, and that's just bad planning or inexperienced somebody somewhere. But it didn't take very long to see that there was a major problem there in terms of the outflow of water. And anytime that I have a client that says, hey, my shower has water puddling in the shower now, I want to avoid that in the new house that you're designing for me, Bob. I put in at least two big drains in there to make sure that the water can get out. And that's a consideration. You want to be very careful that the water that you're putting into something, if you expect it to go away, that you have the capability of making it go away. So although the trap size here is 2 inches as a minimum for a shower, I would say that would be well inadequate for any shower that has a lot of sources of water coming in for part of the shower process. So you want to be careful about that. Now the toilets, the trap is actually built into the toilet, so we don't see one. We don't have to indicate one on our riser diagram, but you will want to, for all of the other fixtures that are in the house plan that I've provided for you, when you do your actual riser diagram, you will want to identify the trap size, the minimum trap size, and the minimum diameter of the pipe that's leading away from that particular fixture. So if you have a bathtub, you're going to show a trap in the riser diagram, and you're going to label it as 1.5 inches, and then the pipe, the minimum, And then the pipe that leads away from that bathtub is going to be a minimum of 2 inches. And that'll make more sense when we actually get to the diagram that shows you what a riser diagram actually is. And that'll come. But do we have any other questions about this as far as the fixture and the trap size and the waste pipe diameter?
What's a water closet flush valve?
I think that is in a commercial building, you might see when you flush the toilet that there is no tank attached to it, that it has a pressure valve on it that actually pressurizes the flow of water into the toilet bowl itself. Whereas a water closet with a tank is just your typical toilet that you see that has a tank of water behind it, and that's where the flow of water comes from in order to flush the toilet. So the flush valve has a much higher velocity of water flow into and out of the bowl.
Okay, thank you.
Have you ever seen one of those? You know what I'm talking about?
Yeah, I know what you're talking about.
Sometimes they don't even sit on the ground or the floor. They're actually mounted to the wall. So there's no actual base of the toilet touching the floor, which is a good design in terms of trying to mop up the floors. You can get, you can mop the entire floor. You don't have to mop up against the toilet itself. All
Yeah, I
right.
really like the wall mounted toilets.
You do or you don't?
I do. I think they're a lot smarter way to do it, a lot cleaner too.
Yeah, I think I agree with you on that point. Absolutely. So let's see. We did talk about that. And now we're going to talk a little bit about the coefficient of linear expansion. And that's, remember I mentioned that materials expand and contract based upon temperature. So there must be, now there is a formula. We have K, which is the expansion. We have L, which is the length. We have again, we have a delta T, which is the change in temperature. So we're going to start with one temperature and measure the length of the pipe. And then we're going to introduce a second temperature and measure the length of the pipe. And then we're going to have a total change in length. It's either going to expand or contract. It's not going to be a lot per length of pipe, because look at the number here. It's 10 to the minus 6. That's a very, very small number. But I would ask you if just to look at this formula, and I would ask you if you could explain this formula in terms of when the temperature is greater than when the second temperature is greater than the initial temperature, or the second temperature is less than the initial temperature, what's happening to the length of the pipe? Is it expanding or contracting? And the whole secret is in this parentheses right here. This is the second temperature. This is the first temperature. This is the initial. This is the final. And you can use that to explain whether materials expand or contract based upon the change in temperature. Does anybody want to tackle that?
I know the pipe should expand when it gets hotter and contract when it gets cold.
That's from practical experience, and you're right, but explain it based on this part of the formula right here. Let's put a value in for T1.
Well, can I say that if your initial temperature is going to be less than your final temperature, then whatever you're working or whatever, it's going to expand. And if
Because
you're,
why? That's going to be a positive number, right?
correct. That's right.
So finish up. Go ahead. Do the option opposite.
So if your initial temperature is larger than your final, then it's going to be contracting.
Right, because it's a smaller number. So if T2
Okay.
equals 10 and T1 equals 5, we have a positive number here, which means that that's going to be a positive number. And if T1 is greater than T2, if this is 10 and this is 5, then 5 minus 10 is going to be a negative number, and that's going to be a negative number, meaning that the change in length is going to be a minus or a contraction. So you're absolutely right. You understood it from practical experience, from knowledge, but you also can explain it just based on this formula right here. When the temperatures are, the second temperature is greater than the first temperature, that means it's going to be warmer than it was originally. Therefore, it's going to expand because the number is going to be a positive number. When you decrease the temperature, when T2 is a lower number, when T2 is a lower number than T1 is, then you're going to have a negative number here, right? T2 is
Correct, that's right.
so this is going to be a minus number. And so it's going to
Correct.
contract. And so let's take a look at the coefficient of linear expansion for various materials. Okay, so steel, 6.5 times 10 to the minus 6. Cast iron is 5.6. So it expands less. Copper, though, look at copper does expand substantially with respect to these other two materials. But look at PVC, it expands way up there, 35 times, or 35 times 10 to the minus 6, which is way greater than 5.6 times 10 to the minus 6. So if I were to give you a question like this on a quiz or exam, I would not make you memorize the coefficient of linear expansion. I would say something like this. I would say a 10-foot length of steel pipe warms from 30 to 140 degrees. So 30 is which, T1 or T2?
30 is T1.
Exactly. And 140 is which, T1 or T2?
T2.
So it's going to be 140 minus 30. So we're going to have a positive number, right? We're going to have 110. That's a positive number. So therefore it's going to expand, which makes sense because we're warming it up to a higher temperature. But we want to know, I would want you to tell me what's the increase in length. So we have the formula right here. Delta L, the change in length, equals the length of the pipe, 100 feet, times K, which is the a coefficient of linear expansion. In this case, we're talking about steel pipe. So we're talking about this one. So it's going to be this one right here. So it's going to be 6.5 times 10 to the minus 6. And then it's going to be times delta T, boom. T2 is 140, T1 is 30. And the 12 inches per foot here is we're simply changing it from feet to inches. So there's 100 feet. How many inches are there? Well, multiply it times 12 inches per foot. That would give you the total amount of inches rather than the total amount of feet. And the change in length is going to be in inches. So it's going to be more than half an inch in expansion. So 100 feet of steel pipe changed from this temperature to this temperature will expand by 0.858 inches based on this formula. So does that make sense to everybody? Now imagine if we had 100,000 linear feet of pipe, then we would use the 100,000 times 12 times this, and that would give us a much bigger number, wouldn't it? So when we have a long distance of pipe, we have to consider the expansion of that pipe. That pipe's going to expand, or it's going to contract. So does this make sense to everybody?
Yes.
Yes.
All right. And so imagine that I'm a developer and I develop apartment buildings and I've been doing it for 50 years. And you're an architect. And I make an appointment with you and I come in to your office and I have one of those Zero Halliburton aluminum briefcases. And we sit down at your conference table and I explain to you, I say, you know, I'm really not happy with my current architect and I'm looking for a new architect. And I'm going to ask you one question, and if you answer that question to my satisfaction, I'm going to open up this briefcase, and I open it up and I show you that inside of there, it's full of stacks of fresh new $100 bills to the sum of about $50,000. And I say to you that if you answer this question, I'm going to ask you one question because I'm not satisfied with the drainage in any of my apartment buildings of the water. I'm going to ask you one question, and if you answer that question correctly, I'm going to slide this briefcase across to you, and that will be your retainer, and you will be my new architect for all of my new apartment buildings that I'm building across the world. And the question I have to you is, what would you recommend that I do to the pipe in my new buildings that I haven't done in my old buildings to my satisfaction? What would you recommend? There's two things I want you to tell me to change about the pipes in the new buildings, the design of the pipes in the new buildings. For the drainage, tell me two things that you would recommend that I do differently than I've been doing now. And I'm going to slide this briefcase across and you have a new client. What are the two things that you would say that I would want to do to the pipe? So you're not getting the job. Well, the answer to that question, you would say, Mr. Bryce, I would recommend that you increase the slope of the pipe, and I would recommend that you increase the size of your drainage pipe greater than what you've been using in the past. And if you had said those two things, I would have slid the briefcase across the table and you'd have a new client for apartment buildings. But does that make sense? If you want the flow of water to increase, slope the pipe, make a greater slope on the pipe. Does that make sense as a practical sense, not a academic sense, but just practicality? Does anybody not understand where that would make sense?
It makes sense.
Makes sense, yeah.
And you would increase the size of the pipe as well, okay? So assuming that I just asked you that question and I haven't given you the answer yet, the briefcase is still on my side of the table. What would you say is the answer to that question in order to get that briefcase slid across the conference room table to your side?
Didn't you just give us the answer, Professor, to increase the slope and change the diameter of the pipe?
Absolutely correct. And then you would just get this briefcase slid across. And I did answer it. Yes, I did. But that is the answer. You know, if you want to increase the flow rate, slope the pipe greater and increase the size of the pipe. Those are the two things that you would want to do in order to get a better flow rate.
So when you say slope the pipe, that means the area around your pipe, you just make a slope like the floor itself. Like if you were doing a drainage pipe in, say, in your bathtub, not bathtub, but in a shower, you make the actual shower floor like in a slope. So it's like a greater slope. That's what you mean, right?
No, the slope of the bathroom or the shower floor would take the water to the drain. But once it gets in the drain, then it goes to the pipe. And once it gets in the pipe, if you want to increase the flow of that water away from the shower drain, then slope it, make the slope of the pipe greater. You know, instead of it being a 2% slope, make it a 5% slope so that the angle of the pipe is greater. And make the pipe size bigger. And that would allow you to get a bigger flow rate as well. So if my friend in Southampton somehow had put larger drains in his shower, but he didn't change the slope of the pipe or the size of the pipe from the normal shower drain, so he just had two drains draining into the same size pipe that didn't have a greater slope, it wouldn't matter. You know, because the water would not be able to drain away any more than it would normally. So those are the two things that I would ask you to think about: change the slope of the pipe and change the size of the pipe. Generally, when you look at a building, there is a floor, and then below that floor there is a drop ceiling, and there's a space between the drop ceiling and the floor above. And so that's the place where the pipe would be allowed to be sloping from one point to another. So you would increase the slope, but make sure that you didn't increase it so much that the pipe actually penetrated through the ceiling. You have to be very careful about that. So that it doesn't, that when the pipe reached the wall, that it was going to drain into a vertical pipe, that it was still above the ceiling, that it wasn't below that. All right, so any questions? Make sure you sign in for the attendance. I'm going to leave you with a question and I'm going to tell you a situation that I had, and I'm going to leave you with that. I don't want you to answer it today, but we'll come back, think about it over the week, and we'll come back with an answer and or a suggestion of an answer next week. But the end of the class today, I'm going to tell you that I had a client once who asked me to design his house for him, and he asked to have 2 laundry rooms on the first floor. Why? I don't know. I never asked why. I just gave him 2 laundry rooms on the first floor. And he built his house. His house was built for him, and he moved in. And he called me up one day and he said, Bob, we love our new house. It's really great. Our housekeeper only uses one of the laundry rooms, but the laundry room that she doesn't use has started to smell, and it smells really bad. And he said, I think maybe my contractor did something wrong. And I had an answer for him. And that's what I'm going to ask you to tell me next week is, what would you recommend to my client in order to eliminate the smell in his laundry room? And I want you to think about that over in the laundry room that his housekeeper didn't use. Nobody used the other laundry room. They only used one. They didn't use the other. So with that, I'm going to say goodbye, and I will see everybody next week. And hopefully at the beginning of the class next week, somebody's going to have a suggestion, which would be a great solution for my client. And hopefully you give the same answer that I gave him, and it did solve the problem. Okay? All right. So I will see everybody next week. Same time, same place. And I do have office hour, before from 10 o'clock to 12 o'clock. If you have any kind of questions, don't hesitate to stop in and say hi and ask me whatever kind of questions you have. I'm available. All right. I'm going to stop it now and start converting the recording, and then upload it as soon as I can.
Thank you, Chris. Have a good one.
Thank you.
Good weekend, Professor.